Okay, so we've got this DC circuit with a 120 volt supply, and then we have it's a series parallel combination here. And before we go on, before we go on, I just want to I guess ask you to think about this and tell me, go ahead and like type it in the chat thing there or whatever. If somebody can tell me just kind of off the top of the head, what is the voltage at node A here? So this node A, yeah, exactly. So that's 60 volts there. So very good. If you could determine that, it's kind of telling you that you're thinking the right ways, that we have, these two are in parallel. Since they're of equal value, they're going to be 10 ohms. And then we have a voltage divider of the 10 ohms here in series with the other 10 ohms. So that's going to split the voltage. So the voltage is going to be, so the voltage here at node A is just 60 volts. Okay. All right. So, so hopefully everybody was able to just kind of look at that and very quickly identify that is 60 volts. Okay. So let's see if we, does anybody want me to work through the reduction of this? I mean, I guess basically, let's see. So basically, if I kind of shift these over here, okay. All right. So as I said, these two in series, or these two in parallel will give me a resistor here in series with the other resistor. And for the parallel equation there, we have R2 in parallel with R3 is equal to the 1 over 20 plus 1 over 20. All right. And so if you put that in those fancy calculators, that ends up giving you 10 ohms. Okay. And so then we have the voltage divider. So we end up with the voltage divider here with our modified circuit. Where we have R1, which is 10 ohms. And this R2 in parallel with R3, which is another 10 ohms. Okay. And so right up here is my point A. And so the voltage here at point A is 60 volts. Okay. And so my current flowing into this, anybody want to take a shot at what the current is? Okay. So the current I is 120 volts. Okay. Yeah, so 120 volts divided by 20 ohms. The O's cancel, and that gives us 6 amps, correct. Very good, Austin. All right, so now given that then, right, if we review power, which I already mentioned, okay, what happened all? Okay. So if we review our power, okay, power in a DC circuit, at least, is the voltage times the current. Okay, so in this here, we're talking about real power, which effectively in a DC circuits is all you have to worry about. But so we have 120 volts times 6 amps. So what is that? 720 watts. Yeah, okay, just wanted to double check here. 720 watts. Okay, so our power is 720 watts, and of course, if we're going to put that in Blackboard, we need to have our 3 significant digits, and since this ends with a 0, you need to make sure that you put your decimal point in there. Okay, so that is our power for the total circuit. Okay, so that is our power for the entire circuit. Okay, so now let's take a look here. What is the power just in resistor R1? Okay, so the power for resistor R1, okay, is the voltage across the resistor R1 times the current through R1. Okay, or we could write that another way as saying it's the current through R1 squared times the resistance of R1. Okay, and yes, correct, Alex. So that's since we've got 10 ohms here and 10 ohms here, and we have a total of 720, then the power for just that resistor, and again, we need our 3 significant digits, so we need to make sure we put that decimal point to make sure that that 0 is considered significant, but it's 360 watts. All right, so that was the easy one. So what about the power for R2? Okay. So if we look at the resistor R2 here, let's see. Just going to kind of move this up a little bit so I have a little more room to write here. And then we're looking at, actually, no, Well, let's look at this resistor. Yeah, let's look at this resistor here first. So this resistance, which is the parallel combo, R2 in parallel with R3. Okay, so that, right, since that's 10 ohms too, right, then that's going to have the exact same thing. So that's going to be the voltage of this parallel combination times the current through it. Okay, and it's also 360 watts. Okay. However, if we go back up to the original circuit, what is the power through just R2 up here in this original circuit? So what is the power of just R2? Well, now we've got to look at the current splitting, and what is the current going through just one of these? Okay, so we already said we have 60 volts here, so we know the voltage across it. All right, so we can get this current through R2, okay, which is correct, Josh. It's going to split in half, right, because these two values are equal. So that current is going to split in half. And so we're going to get 3 amps flowing through that. So the power P2 is now 60 volts times 3 amps, which is 180 watts. And of course, since P3 is the same value of resistance and it's going to have the same current going through it, and that's 180 watts. Okay. All right, so if we look then, what is the total power? Well, we have here these two powers, right? These two powers, which are each 180, add up, right? So these two powers, which are 180, add up to be 360. Okay? And then these two powers, which is the power for resistor R1, and these two added up, gives us our total power of 720 watts. Okay, so the total power another way of determining the total power is simply taking power 1, the power from resistor 1, which is right here, and the power from resistor 2, and the power from resistor 3, and simply adding those up. Right? And so when we look at this circuit, even though the original circuit was a series parallel circuit. Okay. So here was the original circuit, and it's a series parallel circuit. But even though it's a series parallel, so these two are in parallel, power simply adds. This is all the power in the circuit that's being used. Okay, so it doesn't matter whether they're in parallel, whether they're in series, whether they're in some kind of series parallel combination. Total power just is the sum of all the individual powers. Okay. Okay, so, this is really just a review. So before I go any further here, is there any questions about what we talked about right here, about just calculating this power, calculating total power from the sum of the individuals? Or we also found total power, right, by simply using the total voltage times the voltage total current, and that gave us the total power. But again, this was all for a DC circuit. All right, so nobody's saying they have any questions, so let's go on. And we're going to look at the exact same circuit here. Okay, so I'm just going to paste this back in here once. Okay, but we're going to put in, let me just find some clear space here. All right, so all right, so here's the exact same circuit, but now we're going to put AC voltage source here. Okay, so we're going to have this AC source, and it's still 120 volts. Okay, so it's still 120 volts here, but it's going to also have an angle of 0 degrees. Okay, so it's going to be 20 volts, but an angle of 120 degrees. And so now, when we calculate the power, okay, let me just make a copy of this here before I go any further, so I might have to. All right, so now if we look at this, we really get effectively the same thing. So here at point A, so right here at point A, okay, since this is only a resistor here, right, it's going to be 60 volts with an angle of 0 degrees. Okay, and so calculating our power, we actually, all the powers are going to be exactly the same, okay? But this is just a total resistive circuit, okay? So when you try to calculate your power, say P1, so your power for P1 is simply I squared times R1, so that's going to be 6 amps, okay? Angle 0 squared times, oh, I'm sorry, that was supposed to be 10 ohms, wasn't it? Is that, I heard somebody putting in a message there. Yeah, that's supposed to be 10 ohms. This was the original problem from chapter 7 in the book that I pulled out this morning, but I changed the values to make the math easy. Okay, so yeah, thank you. Okay, so yeah, so if I get my resistances right, that is so 6 amps squared times the 10 ohms, right? And so that would be 360 watts. Okay, and 60 volts divided by the 20, or 6 amps. 6 amps are going in. 6 amps are going through R1, but that leaves 3 amps for the 220 ohms, right? So powers 2 and 3, right? Those are equal, and those are 3 amps squared, angle 0, times the 20 ohms, and that gives 180 watts each, right? So power total is the 360 plus 180 plus 180, right? Which is going to give me my 720 watts total. Okay. So this is totally resistive here. So this is a totally resistive circuit. And so it really doesn't matter whether it's AC or DC. The power being used, well, since the voltage is the same, and once I got all my resistance is the same, the power is the same power being used. So, but remember here, we are using the polar form of the voltage, which means that this voltage is RMS, right? So this was an RMS voltage here. All right, and so if you remember the whole kind of point, the whole kind of point of the fact that we use RMS voltages for the phasor is that it is equivalent to the DC. Okay, so if we were to calculate this using the time domain representation, okay, then our voltage, okay, if we look at the time domain of our voltage, all right, that ends up being square root of 2 times the RMS, okay, and the same with the current. So the current would be I times the square root of 2 you know, and then of course there's a sine wave here, sine omega t, whatever omega t T is they didn't really give us omega for this circuit here. Okay. So if we're going to look at the time domain, yep. Guess there should be an R up here somewhere. RMS times the sine of omega t plus this phase shift. Okay. So now, I mean, in this case, it's all resistive. So, you know, so the phase shift was simply 0. Okay. So phi is equal to 0 in this case. Okay. But the general form, okay, the general form for power, okay, if we're using like the time domain, we would have the total power. We would have to calculate this as being, right, so if we would have here the square root of 2 times VRMS times the square root of 2 times R times IRMS times the cosine of the phase angle between the two. All right, but see, now we have the square root of 2 and the square root of 2, so we actually have to divide. Okay, to get power, we got to get rid of these square root of 2s. So we effectively got to divide by the square root of 2 times the square root of 2. Okay, now remember that this is the peak value of the voltage, and this is the peak value of the current. All right, and so the thing is that we need to get, the whole point of the RMS was that the RMS was giving us a DC power equivalent. All right, and that's why I'm dividing by these two square root of 2s. Okay, and of course the square root of 2 times the square root of 2 is simply 2. All right, so if you're looking at calculating the power, if you're looking at calculating the power for a AC circuit, okay, so the power for an AC circuit, you have the power is equal to the peak values I'm kind of trying to write this up, and I'll put it in here. V peak divided by 2 times the cosine of that phase angle. All right, so if we look at this, just kind of write it up a little bit better here for you. So you have the V peak times I peak divided by 2, because that's canceling out. All right, you got a square root of 2 and a square root of 2, and that's canceling out that. Okay. And then you have this phase angle phi here, okay, which in the circuit so far that we've done, the phase angle was simply 0, and the cosine of 0 is 1. Okay, so the cosine of 0 is 1. Okay, and so if it's 1, you got 1 times these values. So this is the power equation. This here is the power equation for the time domain, using the time domain or the peak voltages for the current. Okay. So you have to, if you're using the peak values, you have to worry about the fact that there's a square root of 2 in there, so you have to divide by 2. But if you're using the RMS value, you basically are divided by 2, and so you don't have to worry about it, because that's what the RMS value is doing, is giving you the DC equivalent. But you still have to worry about this cosine term. All right, and I'm going to show you that a little bit in a little bit more detail. Okay, and so let's take this circuit that we have right here. Well, I'm just going to modify this. So this was our original circuit, okay, effectively. But what I'm going to do is I'm going to throw in a capacitor. Okay. So we're just going to kind of come over here, and I'll just throw in a capacitor. And I'm going to calculate the current in that capacitor. Kind of make that look like a sine wave. So I'm gonna, it's not a very good waveform there, but, or parallelogram piece there, but, so I'm just gonna kind of make this circuit here, okay? And so now if we look at this circuit, all right, we have these two which are in parallel, and these two which are in parallel. Now I guess I need an impedance there. So let's just let's try and make it easy. It's not going to quite work so well now because it's a capacitor, but let's just make this 10 ohms also. All right, so here is a circuit with some reactance in it. Okay. Now, if you remember, right, reactance, what does that do? Well, capacitors and inductors store energy. They don't use energy, they store energy. And so therefore, what the capacitor is going to do is during like that high side of the sine wave here, it's going to be putting charge inside of the capacitor, or inside of the electric field within the capacitor, technically, right? So in here between these two plates, we're storing that energy. Okay. But now when the sine wave changes direction, then we're going to take that energy out of here. All right, so we're going to kind of take that energy out. And it's kind of fed back into the circuit and goes the opposite direction, and then we're storing it in the opposite direction. Okay, so during the one half of the cycle, we're taking this and we're putting it in, and then during the second half of the cycle, it's coming out, going back through the power supply and coming in, and then we're storing it in the opposite direction. All right, so for the capacitor, we're just continuously taking this energy, putting it in, taking it back out, and putting it in the opposite direction. And that's what the capacitor is doing. So it's not using energy. So when we talk about power, P, this capital P up here for power, right? When we're talking about power, we're talking about power that's being used. Okay, so remember, kind of power being used is kind of like saying the power power being used is like talking about it's being converted from this electrical energy into some other form, which with resistors is basically thermal energy, turning it into heat. Okay, so I've got my 10 ohm resistor here. Looks like I lost that. So I've got my 10 ohm resistor, or yeah, I've got my 10 ohm resistor, and I also have my 10 ohm capacitor in here. So now we can simplify this circuit to calculate the total current. We come in here and simplify the circuit. So we'll take these two, which are in parallel, and we'll take these two, which are in parallel, and that'll just give me a couple of parallel impedances here. Okay. We'll just kind of call those Z1 and Z2. Okay. So we have here Z1 and we have here Z2. Okay. And so Z1 is going to be 1 over a minus J, because remember, this is a capacitor here, so effectively there's a minus J there. So it's 1 over minus J, (10 ohms) plus a 1 over 10 ohms. Okay. And so if we calculate that, that's going to give us something like the square root of like 7.7, I think. Let me just double check it. Z1 is 1 over and then we need to calculate. Okay, so I'm using the Octave software here to calculate. And remember, when you're using Octave, you always have to, it always gives it to you in rectangular. So I'm also just going to put it in polar form so we can kind of see that there. All right, so yes, 5 minus J5, correct. Okay. All right, so when we look at that, okay, so when we look at this, this is Z1, okay? So Z1 here is 5 minus J5, okay? And Z2, of course, is a little bit easier because okay, so Z2 is 1 over 1 over 20 plus 1 over 20, which of course is just a simple 10 ohms. Okay. All right. So that gives us this equivalent impedance here. All right. So by looking at Z1, okay, Z1 technically in here, even though it's in series now, but there's a capacitor in series with a resistance. So there's a capacitor in series with a resistance, and Z2 though is all resistance. Okay. All right, and but I kind of wanted to point out the polar form of this, right? So here is Z1, which is 5 minus J5. And of course, the calculators, they always give you I instead of a J, okay? But if we look at the polar form of this, okay, what we see is it's 7.07 amps, or I'm sorry, this is ohms, at an angle of minus 45 degrees. Okay, so we have this minus 45 degree in here, but that's only for the J1 term. Okay, so that's only for the J1 piece. But then for the Z2, right, that's an angle of 0 because that's just resistance. Okay, now, but now these two are in series. So now we've got these two here, which are in series. Okay, so our total impedance, becomes Z1 plus Z2, okay, which is a 5 minus J5 plus 10, which gives me 15 minus J5. So that is my total impedance. Okay. Okay, so this is total impedance here. Put a box around that so we can find out later. So this is our total impedance for this circuit. And so if we look at the angular form of that, just calculate the angle form of that. Yes. All right. So all right. I appreciate you guys calculating that. So yeah, so we got 15.8 at an angle of minus 18.4 degrees. Okay. And so that is our polar form of that. Okay. So now, if we were to draw the Phasor diagram, all right, so I want to remind you of Phasor diagrams here, or in this case, it's going to be what we call the impedance diagram. So we have the impedance diagram. Okay. So we're going to draw the impedance diagram here. All right, and so looking at this impedance diagram, for the total impedance, okay, we have make that a little bit wider there. Okay, so we have our resistance term, which is 15, and then we have about a third of that, and this isn't going to be quite to scale here, but we have about a third of this. If this is 15, say about a third of that would be this. Okay, and so that gives us our total impedance right here. Okay, so this would be the impedance diagram where we take minus J5 is right here. And 15 is here. Okay, and so our complete impedance is 15 with an angle of minus 18 degrees. So if we look at this angle right here, all right, that angle is this minus 18.4. All right, so this is the impedance diagram for the circuit here. Okay, so is there any questions about that? Okay, so we have the resistance. Let me try to expand this out a minute here. Should have drawn it a little larger. All right. Okay, so Austin, wouldn't you leave that in rectangular form even though you converted it for the angle? Well, I wanted to show you, okay? For the most part, I usually like to keep it in rectangular form. That's correct, because the rectangular form gives me what the resistance is, okay? So, the rectangular form shows me what the resistance is and what the reactance is, okay? So the resistance is 15 and the reactance is 5, and that's correct. So the hypotenuse is the total here, okay? So the hypotenuse is the total impedance, okay? But so this part right here, right, this is the hypotenuse, that's the total. Okay? But this angle, this phase angle, becomes very important here when we're talking about power, because the phase angle tells us how much of this how much of this is going to be stored within the capacitor piece, and how much is actually going to be dissipated through the resistances in the circuit. Okay, so now let's go ahead and calculate. This was our Z total. Okay, and when you're doing your calculations, you can use either form, whether it's rectangular form or whether it's polar form. Okay, so but now looking at this, if we kind of redraw the circuit, okay, so if we redraw the circuit, right, I have my voltage source over here, and I have a resistance. It's supposed to be a resistance here. Okay, I have a resistance of 15 ohms, and then I have a capacitor of 5 ohms. Okay, so there is my total circuit. So that is effectively my total circuit here. So now using Ohm's law, we can find our current. Okay, so using Ohm's law, we can find that the current, so the total current here is equal to the voltage source divided by the total impedance. Okay. All right, and so my total current is equal to 120 volts angle 0 divided by the 15 minus J5. Okay, and so all right, so Austin is telling me that that is 7.59 amps. .59 amps at an angle of the 18.4 degrees. Okay. So does somebody concur with that? All right, excellent. Thank you, Zach. So, All right, so everybody's agreeing with that. So one of the key points that I sort of want to point out about this is the fact that this here is a positive, right? Because there was a negative here, and we're dividing by the negative, and so that gives us a positive. Okay. All right, so given that, okay, we can calculate the total power, okay, and this is all phasor form, so our voltages and our currents are in RMS. Okay, so we could calculate something we call total apparent power. All right, and so I'm actually looking in the book here on page 873. All right, and they give us that the power is S is equal to V times I. So we've got a new variable here. Okay, so we have this thing called apparent power. Okay, and so apparent power has a different variable S. Okay, so we have apparent power, which is S. We have real power, which we've already talked about extensively. We have real power, which is P. Okay, this is the power being used, being converted into heat if it's for resistors. Okay, or being converted into something else. And then we also have something which is called reactive power. Okay, and so we're going to need a new variable for that also, and that's called Q. This is the power being stored, okay, inside of either a capacitor or the inductors if we have inductors. Okay. All right, so apparent power is the power that it looks like we're using. So okay, so the apparent power S is the power that it looks like we're using. And real power is the power we're actually using. And reactive power is that energy that's being stored. Okay, but the key point here is that this is highly associated with our impedance, right? So if we take this impedance diagram here, okay, so we have this impedance diagram, and so when we start looking at these, okay, this is the impedance diagram over here, but we're going to create what we call the power triangle. Okay, and so we're going to create a power triangle, which is essentially like the impedance diagram. And the only real difference is that the units are different. Okay. So let's talk here a second about units. Okay. So the units of apparent power, well, we know that the units of real power are watts, right? So we know that P is equal to the voltage times the current, all right? And then there's also this cosine of the angle here, of the phase angle, right? But the units of this is watts, right? Which technically watts is volts times amps, or volts times amperes. So when we look at apparent power, the units, okay, well, the equation for that, I'll just give you the equation is the voltage times the current starred, okay, and that the units of that are actually given in volt amperes. Or VA if you want to abbreviate it. Okay, so the units of apparent power is volt amperes. Okay, and the units of reactive power, okay, so the units of reactive power here are Q is equal to P power, or excuse me, Q is equal to voltage times current times the sine of this phase angle. All right. And so the units for this then are given as volt ampere reactive. Okay, and so usually you see those kind of written as VARs, okay, or you hear the term VARs, all right? And so when we look at this, we have here Q is volt amp reactive, and power is in watts, as we've always talked about. But now we have the total apparent power, which is the combination of the two. Okay, so the apparent power is the power being used within the resistance and the power being stored within the reactive portions of the circuit. Okay, and so yeah, what does that star mean? That's an excellent question, Andrew. Okay, star, it means complex conjugate. Okay, and they talk about this actually a couple of pages later. All right, so if you notice on, if you're looking in the book on page 873, you notice they have the S is equal to V times I, but it's not bold. Remember how I talked before about bold lettering is indicating of a vector? What they're looking at on page 873, they give you the equation 20.6. Okay, so equation 20.6 in the book, they simply say S is equal to V times I. But what they're not showing you is that there's a vector there. All right, so technically what I gave you here is the equation a couple of pages later. If you look on page, like, say, 879, they give you a capital, they give you bolded S. It's bold. And they have S is equal to P plus Q. All right. And so when we talk about the power triangle here, okay, we get that S is equal to P plus Q. All right, but these are vectors. Okay, so these are vectors here. Okay, so up here in this equation, they're ignoring this phase angle. All right, don't forget about this phase angle here, but they're ignoring the phase angle up here in this equation. Okay, but if you look at it this way, we're looking at the phase angle. Okay, so what I want to do here is I want to calculate the total power. Okay, so we'll come over here, we're going to calculate the total power, the total apparent power with the phase angle. All right, so we know up here we have I total, and we have our E, right? This was our E up here. So we can calculate the total apparent power in a couple of different ways. Okay, one way is, as I just showed you here, right? This is my total apparent power, which is the vector V times the I, but I know I haven't answered your question yet, Andrew, but we have this star here. Okay, star the star means complex conjugate. And that complex conjugate, that's over on page 881, where they give you that full equation 2029. All right, and they show you that star, and they talk about this. But if your current is an angle of plus 18.4 degrees, then the conjugate is minus 18.4. Okay, so, or looking at it another way is looking at the rectangular form. So if you look at the rectangular form, okay, so if we looked at the rectangular form for, say, our impedance up here, okay, we had 15 minus J 5 ohms. This was our impedance. So the conjugate of that would be a 15 plus J ohms. So what you're doing when you're talking about these conjugates is you're changing the sign of the values. So it doesn't matter whether you're in polar form or whether you're in rectangular form, but you're changing the sign that is effectively your phase angle. All right, and the reason they do that, it's kind of hard to understand, I guess, but the reason they do that conjugate when you calculate apparent power is we want the phase angle of the power to be the same as the phase angle of the impedance. And that's why I added this impedance diagram down here. Okay, so this was the impedance diagram. So let me just maybe label that again, right? So this down here was the impedance diagram. Okay, so this piece was the impedance diagram, but the power triangle is effectively the same as the impedance diagram. So when we look at this, you can calculate, you know, S is equal to P plus Q, or we can also calculate it using the V times I conjugate here. So since at this point, right, we have that our total current is 7.59 plus 18.4 degrees, okay? So, and our E was simply the 120 volts, right? So we can calculate our total power S, okay, gives us E, our total apparent power, I should say, S, the total apparent power, is our 120 volts at an angle of 0 degrees times our current, 7.59 amps at an angle of, but this is the conjugate, okay, so I'm putting in a negative here, negative 18.4 degrees, okay, and so again we have this negative just trying to highlight this, okay, so this guy is negative because of the star up here. Okay. Right. So then if we calculate that, that'll give us our total power. Okay, so what you got there, Dan? Okay, so yeah, so 900, effectively 911, yes. Okay. All right, so here are my calculations out of octave there. Oops. Let me show the first calculation. Okay, so the octave program, of course, gives us in rectangular form, and then we have to convert it. But, all right, so the total power is 910. Now, remember, the units for this are volts times amps. Okay, so my units are VA, volt amperes. Kind of hard to write freehand here, but the units are volt amperes. Okay, and so this is the total power. And as you guys pointed out, it's like, yeah, if we go back and we look at our original circuit, okay, way up here we had 720 watts. Okay, but our total apparent power is more than that, because that's why we call this apparent power. It looks like we have more. Okay, and we do have more power in the circuit. We're just not turning it into heat. We're not using it. It's being stored in that capacitor, right? And so the power is there, but it's being stored instead of being used. Okay, and that's why it is more than what we had before. So now let's come back and look at the real power up here. All right, if we look at this, right, we have V times I times the cosine. Okay, so we have V times I times the cosine. My V and I kind of got chopped there a little bit. Okay, but so if we look at the total power is V times I times the cosine of this phase angle. So here my phase angle is 18.4 degrees. Okay, so if we calculate this, then we calculate the real power. Is V times I times the cosine of this phase angle. Okay. By the way, we did a little bit of rounding here. We've only been using 3 digits for that calculation, so it might be off a little, just a hair. But and also, just so you know, this would be the same even if it was a positive angle. When you're doing a cosine, when you're doing the cosine, it actually doesn't matter whether it's a positive or a negative there. All right, because the cosine actually turns out to be identical. Okay, and if you do the sine, the magnitude's always the same. It's just we'll have the negative sign, but the cosine, even if it's positive or negative, the cosine of these always turns out positive. All right, so I'll kind of show you that here. But this is our real power. So we're going to do this calculation that we had up here. Now the voltage and the current here, the voltage in the current piece right here is just the magnitude. Okay, this is just the magnitude of those. Okay, so this is just the magnitude. And so we just have our real power, and I'm going to just kind of do both calculations to show you there. I'll paste in here. So we have the 120 times 7.59. Now the reason it's just the magnitude is we're not ignoring the angle. Right here's the angle in the cosine. Okay, so we're not ignoring the angle, but here the V and the I is just the magnitude piece, and then we're calculating that difference of that phase angle with the cosine term. So it's not like we totally ignored that. But cosine of minus 18.4 degrees. Okay, and since I'm doing this in octave, I'm going to have to scale it to radians. Okay, but I'm okay. I'm going to do the positive one too, just so you can see that it doesn't change your answer. Okay. Now, when you look at this, this is not going to match up to the 720. Okay. It's a little bit larger than that. And then remember, of course, the units for that. This is power, so the units for this is in watts. Okay. But yeah, so you notice that it's a little bit larger than that, than the 720 in the original circuit. So the original circuit, we had 720. But now that we've got a capacitor in here, where'd the circuit go? All right, now that we've got a capacitor, remember as this impedance, or as this reactance here is storing this energy, okay? Now remember, as I talked about this before, okay, here it is. Here's this energy, and it's coming back, and we're putting it back in. However, watch what happens, right? As it comes out here, we go back into the power source, and then we come out of the power source, and we're going in the opposite direction, back to that capacitor. What's happening here? And it's going through both of these, okay? But it's going through this resistance to get back there again. So we've stored the energy. We took the energy out of the source, put it in the capacitor, and stored it. And then we took it out of the capacitor, and we brought it back through here, and then we take it up through these resistances back into this capacitor, but some of it is being heated up, right? Some of this extra is being stored in there, and that's why it's different than our original circuit was. Okay, so our original circuit, we had 720 watts, but now by putting a reactance in here, we're storing energy in here, sure, but what's also happening is we're using more energy, because, like I say, as we run this through here, and we put it in here, and then as we take it back out and we try to stick it in the other direction, as this extra energy, some of this energy we had stored in here is now running through this resistor, so some of it's going to get lost before it gets stored. Okay, which means that this power source is going to have to give us more energy to charge this thing back up to where it was originally. Okay, and then we take this back out. Now we're taking it out, and we got to run it through resistors again, back through our power source, and back into the capacitor. Okay, and that's why in the original we had 720 watts with nothing but resistors, but by simply adding in a reactance, we've now increased our power usage. Okay, by throwing in that capacitor, we're actually using more power than we were before. All right, so anyhow, that was our real power. And then if we come up and we grab our Q piece, okay, so if we come up and we grab the Q piece here, right, Q is the energy that is stored. Okay? And so Q is the energy that is stored. V times I times sine of this angle. All right, and that I'm getting minus 287 volt amp reactives for that. Okay, yes, Austin, the positive or negative does matter for this because you see the sign here. Here is the sign of the angle. And so it definitely matters. Okay, but the only difference is if you put a plus sign. If it was a plus 18, then you would end up with a plus sign. Okay. Yeah, as Andrew points out, it's an odd function, which means it tracks the sign. The magnitude would not change, but the sign definitely does. And by the way, let me write down the units here. This is volt, ampere, volt ampere reactive, which we usually just refer to as VARs. Okay. All right. So now if where'd that equation go? Okay, so here's this equation right here. We have S is equal to P plus Q. All right. But the Q has actually a J term on it. All right. So the Q actually has that J term. Okay. The power is like resistance, which has no angle. Q is the reactive piece, and the reactive piece always has a J in there. All right, so that's why we have these lines above here, right? These lines are indicating that it is a vector, all right? And technically the P is always real, so it's always a phase angle of 0. And the Q is always an angle of minus 90. So now if we tried to like draw this, okay, so I'm going to draw my reactance piece. Okay, so here's my reactance piece, and I'm going to try to do this to scale. Okay, so I'm going to take this right here. Okay, so you only use the conjugate when you're calculating apparent power. When you're calculating apparent power, you use the conjugate of the current. That's the only time we use the conjugate. Okay. All right, so went too far then. All right, so this is going to be my angle here. or this is my Q. Remember, the Q is, it's actually negative. Okay, so the Q is negative, so that's why I've got it pointing down. Okay, Q is negative, so it's pointing down. Well, you use the resulting angle, Daniel. So the when I used the conjugate up here, I used this conjugate, right? And then that gave me my angle. So when I did the calculation, that gave me the angle as negative. Yes. So you use the sine, the resultant sine of this angle right here. This was your conjugate angle, right? And so that gave us that angle here. That's why this is a negative on our Q. That's why the Q is pointing down. Okay. All right, so I'm going to do the power triangle now. Okay. And so this is my, I'm going to take this 1, 2, 3 of these. And the reason I'm taking 3 is, remember my original impedance, all right? But all right, so this down here is the power triangle. Okay. All right, so this is the power triangle where we have the Q, I have Q, and I have P, expand it up a little bit, but I have P, Q, and then I have my S piece, which is right here. And so S was that original, okay, and the P is right here. Okay, and so S is my total, which is right here. And this 18 degrees gives me my phase angle right here, minus 18.4 degrees. Okay, so here is the power triangle. And over here is the impedance diagram. Okay, and so when you look at these two, they are effectively the same. Okay, so the impedance diagram and the power diagram basically look the same. All right. So if we do it mathematically through the Octave software, right, we can take that P plus Q should equal S. All right, so this is our I'm running into the original circuit we started out with DC down here. Clean this up a little bit. All right, so if you see here, right, this is S. Okay, and S is 864 minus 287. And then if I take P plus J times Q, I should get the exact same answer, right? So these two are exactly the same. Okay, Austin, you got 911. You're looking at the magnitude, right? So, yeah, so if you look at the polar form of this, I would say up here it's 910.8. So when we go to 3 digits, you're talking about this number right here, the S term in polar form. We have 910.8. So if you take out the 3 digits, it would be 911. Okay. So this is the rectangular form. This here is the rectangular form. If you take and go to the polar form, that's your polar value. Okay. All right, so, but the idea here is the fact that power, we have real power, P, that's the power being used in the resistance. Okay, that's the power being converted from electrical energy into heat, into thermal energy. And then we have Q, and Q is the energy being stored inside of your capacitance, or if you have it, an inductor. And so when you put those two together, if you add those two together, we end up getting the power triangle here. Okay, and that gives us apparent power. Okay, so the apparent power is the total power in the circuit. So let's go back and just look at the circuit again. All right, so here was our original circuit. Okay, and so in this original circuit, we had the 3 resistors, the 10 ohm resistor, and then the 2 20 ohm resistors. But then I added this capacitor in here. And again, so this capacitor is storing this energy. During part of the cycle, the energy comes in and it's stored. But then that energy, during this other part of the cycle, that energy comes down through the power, through the resistors, back into, and we store some more, we store energy back into, So we are storing this energy then back into our capacitor, but some of that was stored had to go through the resistor and then got used. And so then the power supply, the power source had to supply more power to charge this back up to the same charge that it was. And then when we take it out, it's got to come back down through these resistors, up through the power source, and then some of it's going to be stored here again. But again, some of it is going through these resistors and is turning into heat. So in the first circuit with no capacitor, we were only using 720 watts being converted into heat. But now we're storing energy locally in the local circuit, part of the cycle, and then we're passing it back around. And as we pass it back around, we're losing some of that was stored in each cycle. And so therefore, we end up using more total power. So if you remember, our total power then, instead of being 720, it was considerably more than that. It turns out being, over 864 watts. Okay, so that is what happens when you start adding in reactance into a circuit. Okay, it doesn't matter whether it's a capacitor or an inductor, you're still storing that energy locally in the circuit. And during part of the cycle, then you pull it out and you try to shove it back in the other way, but some of it is going to be lost. So you're going to use more total power with that reactance in there.